Representation learning is an approach in machine learning that focuses on automatically discovering meaningful patterns or features in data without explicit human intervention. It aims to learn a suitable representation of the data that captures its underlying structure and can be used for various tasks such as classification, prediction, or generation. In this section, we will talk about the difference between vector and embedding, distance measurement, character embedding, word embedding, contextual embedding, and sentence embedding. In the context of machine learning and natural language processing, both vectors and embeddings are used to represent information. While they share some similarities, they serve different purposes and have distinct characteristics. Vectors are mathematical representations of entities in a multidimensional space, while embeddings are learned representations that capture semantic meaning and contextual information. Embeddings are typically more powerful and expressive for various natural language processing tasks, such as word similarity, document classification, and sentiment analysis. In general, we may use dimensions such as 256, 768, 1024, or 2048 to represent a single entity. However, as humans, we are unable to comprehend such high-dimensional spaces. Therefore, we often reduce the dimensions to 2 or 3 in order to visualize the data. For instance, in the figure on the left-hand side, 2 dimensions are used to illustrate the differences among animals. Distance measurement plays a crucial role in quantifying the similarity or dissimilarity between words, sentences, or documents represented as embeddings. Embeddings are numerical representations of words or texts in a high-dimensional vector space, where similar words or texts are expected to have similar vector representations. We will cover some typical measurements such as Euclidean distance and cosine similarity. The choice of distance measurement depends on the specific NLP task and the nature of the data being analyzed. Different metrics may be more suitable for different scenarios, and it is important to select the appropriate metric based on the problem at hand. These distance metrics are used in various NLP applications, including text similarity measurement, document clustering, information retrieval, and recommendation systems. By quantifying the similarity between embeddings, these metrics enable NLP models to perform tasks such as document classification, sentiment analysis, and machine translation. Character embeddings are constructed in a similar fashion to word embeddings. Instead of embedding at the word level, the vectors represent each character in a language. For example, instead of having a vector for the word bunny, there would be separate vectors for each of the letters B, U, N, and Y. While character-level embeddings may not have the same depth of meaning as word embeddings, they have advantages in handling new slang words, misspellings, and infrequent words. Word embedding is a technique used to represent words as real-valued vectors in a lower-dimensional space. It captures the semantic and syntactic relationships between words, allowing machines to understand and process human language more effectively. Each word is represented by a vector with tens or hundreds of dimensions. These vectors are learned from large amounts of text data using various algorithms, such as word2vec, glove, or fast text. The goal is to create vector representations that capture the meaning and context of words based on their usage patterns in the data. Word embeddings are widely used in various NLP tasks, including text classification, sentiment analysis, machine translation, information retrieval, and question answering systems. They have significantly improved the performance of NLP models by enabling them to understand the meaning and relationships between words. Contextual embedding is a type of word embedding that takes into account the context in which a word appears in a sentence or document. It aims to capture the meaning and nuances of a word based on its surrounding words and the overall context. Unlike traditional word embeddings, which assign a fixed vector representation to each word regardless of context, contextual embeddings generate word representations that are context-dependent. This means that the embedding of a word can vary depending on the specific sentence or document it appears in. The advantage of contextual embeddings is that they can capture the multiple senses and usages of a word, as well as the syntactic and semantic relationships between words in a sentence. This makes them particularly useful for tasks that require a deeper understanding of language, such as sentiment analysis, machine translation, question answering, and natural language understanding. Sentence embedding is a technique used in NLP to represent entire sentences as fixed-length vectors. It aims to capture the semantic meaning and context of sentences, enabling machines to understand and process natural language at a higher level. Unlike word embeddings, which represent individual words, sentence embeddings capture the overall meaning and nuances of a sentence. They are designed to encode the semantic essence of a sentence into a vector representation, allowing machines to grasp the subtleties of human language. It's important to note that different sentence embedding techniques may have limitations in capturing the full context or meaning of a sentence, especially in tasks that require a deeper understanding of the surrounding context or document-level information. Representation learning is an important approach in machine learning that focuses on automatically discovering meaningful patterns or features in data. It offers several benefits, including automatic feature extraction, transferability, improved generalization, and reduced dimensionality. By capturing the underlying structure and patterns in the data, representation learning enables machine learning algorithms to perform complex tasks more effectively.